So are we live? Yeah. So great. So let's get started. So welcome back from the snow. So I decided for some strange reason on Monday to still give the lecture. So like 30 of you were so got the announcement and were like watching online. So and I think like over 170 views on the video. So I think that was probably good. I guess not everyone, because of the snow. If your kids were home or something, you may not have been able to watch. So I apologize if this has caused extra trouble. But I thought it was good to do this just to keep us on schedule. If this had been a different lecture, I may have tried to kind of skip a lecture later on. But you know, this homework, which I posted recently on clustering, I think is probably the one that probably will take the longest out of probably all the assignments. For some people, maybe one of the first ones might take longer if they're still getting up to speed on a lot of the concepts. This one asks you to implement and to use several different types of clusterings and try and compare the results of them. And so it's just it's taken students a bit longer, so I didn't want to kind of compress this time frame or push the timelines of these back just with the schedule. Yeah.
Does it take a lot longer to do the work or longer to like execute in runtime and debug?
So in this case, it's more like do the work. The run times of everything should be should be at most a second, I would think, right? That the largest data set's like 1,000, and for those algorithms, the runtime should like basically be linear in the size, right? There's the data set to size, I think, with 19 data points, and that algorithm might take longer to run, but it's 19 data points, right? So it shouldn't take that long to run, but it's a bit more. There's more different things I'm asking you to do, and in the past, students said this one has taken longer. So just an FYI. Okay, that one is posted like on request, because of the snow, I pushed the locality sensitive hashing homework that's due today. It's not marked late in Canvas until like 11:59 tonight. Okay, so I wouldn't push it up to the deadline, because who knows with Canvas all the way, but in case the snow caused some issues, it gives you a little bit extra time to do that. All right. Then I post this on the announcement, but the office hour locations have changed. I've updated them on the web page here. They're still in the same part of the building, but those offices, they decided like on the morning of the office hours that they were going to start remodeling them and then repurpose them for something else. So we've been moved to other offices. I think these are basically just around the corner from where the old ones are. The times are the same. All right, but if you haven't seen that, sorry for the confusion. Okay. And then the data collection report, let's see, in a week from today, the data collection report for your project is going to be due. You should have all gotten some limited feedback on the proposals. Most of them So seem good. If there are lingering issues with those, please come and ask me about them. So hopefully everything is resolved completely by the time you turn in the data collection report. If you do want to change your project later, that's always an option. So this will be due in a week, and it's one of these things like the last part of the project. There's going to be some more like subjective grading on it. Because some people are just going to do a whole bunch more work than other people in the class. And I want to give those people more points. They're going to do better. But for these parts, you basically need to follow the requirements. If you follow those, you make an attempt at those, you're going to get the full credit. A couple people lost points on the proposal because they did not get permission to work as a one-person group, and they turned in a one-person project and small things like that. But otherwise, you should be able to get like the full points on this. If we look at, let's see, where did we go? Okay, so what do I want you to do for the data collection report? Basically, it should be at most 1 page per group. So if you have a group, you are only going to turn in 1 document and still only 1 page, no matter how many people are going to be in the group. And at this point, I just want you to kind of get started and try and collect what you think will be the data that you need for the process. If you're like scraping something off of Twitter, maybe at least get that process so it's tried to be started running. You may need to scrape it for a while, right? But you know, I want you to get started on this so at the end of, you know, when you're actually doing the analysis later on, you aren't then also looking for data. Sometimes this takes longer. For some groups, this is going to be very easy. There's a data set online that you're based on, and you can just download this data set, and you know that's great, right? But okay, but for other groups, this is going to take more time, and it could be that you're not going to complete this by the data collection report, and this takes up maybe 30% of your overall project, and then I won't expect the rest of it to be quite as large if this becomes a more challenging task. Okay, and so, you know, part of this is just some basic information. How do you obtain the data? How large is your data? And this is more, we want to be able to make an assessment. Is your data going to be large enough for the task you want to do? And it's hard to know. There's not like a fixed number of data points it needs to be, but it will depend on what the analysis you want to do. The more complicated analysis, you might need a richer, larger data set, perhaps. But then the algorithms you want to run cannot be as time consuming. Okay, and then what format are you storing your data? This is sometimes a confusing question for people. I want you to think about the abstract data type. Is it going to be, are you treating these as vectors, as sets? Have you converted it? Are you going to convert it in some way? I don't just want to stay, if you store it in an SQL table, that's probably okay, but I want to know how you want to think about it kind of mathematically as a vector or a set or a matrix or in some way like that. That's really what I'm asking here. Okay, what's kind of the mathematical representation, and this will govern what sort of algorithms you can run on top of it. Okay, it could be a graph. Those are other options. And then kind of the part 4 is that you need to process it, do some representation. If you're going to explore different types of k-grams or something like that, talk about that there. Right? You might not need to be doing something. It might come in a good representation, but it might not. Okay, and then the 5th question is pretty open-ended, but I just want you to think about this again. How would you simulate similar data? Sometimes you're going to have a fixed data set because that's all the data that's been collected on this, and there's just not a lot of data. But you might this might end up effectively artificially limiting what you can do with the project. So you want to think about, if I wanted to see how my technique would scale if I had more data, how would you make data that look kind of like the data that you actually have? Okay, and this is important. It kind of makes you think about what properties you think are important about the data by thinking of how you would simulate new data. Okay, yeah?
Can you give an example of what you would mean by simulation?
So Right, so there are some things we'll talk a little bit later in this class having to do with graphs, for instance. Let's say I want to run some analysis on a graph. How would you think of creating a large random graph that's not just every edge is equally likely, but has more structure to it? Right? If I want to create data sets and run a clustering algorithm on the data set, I'd want to create the data set so it has clusters. So I don't just want to put uniform points in a box necessarily. I might want to insert clusters by putting clumps of points here and there, for instance. So how would you do it to like maybe see if your algorithm worked or not, because you know that it actually has the structure you want? If you want to do regression, you want to pretend there is some linear polynomial model with noise and generate data according to this model, and then run your regression algorithm maybe with some outliers and see how it works. Can you simulate data that looks like that? Right? So those are the kind of the things that make sense once you're in this abstract representation. If you're just thinking about, oh, I've got an SQL table, it's harder to think about these sort of answers. And that's the sort of thing I want you to be starting to think about at this stage. And if it's some techniques we haven't really talked about yet, it's understandably you may not have all the answers there, but I still want you to try and start thinking about this. I'm hoping this is something you can do even if we haven't gone through those techniques yet. Okay, so it's kind of a way to get you rolling on stuff earlier in the semester instead of all at the end, even though we haven't gone through nearly all the techniques we're going to for the course. Okay, great. I think crashed again. Okay, I think that was all the announcements I had to do. If there are any questions about the lecture I gave, the way I recorded had to be, I thought I could do a better setup, but I had to hold my phone while I was writing, and that didn't allow it to have any comments on the YouTube channel for whatever reason, even though I had that open. But so I couldn't take any questions during that lecture. Basically, the main. Oh, yeah.
Yeah, sorry, if we could get it. I just was wondering if we could talk more about in DBC and how we built that initial kind of graph of points in the cluster, because I wasn't really clear on what exactly we're doing. We're making all these circles and then finding the, what are they called, core points?
Yeah, sure. Let me go to this quickly. Okay, here's the picture from the slide. It got a little messy, but they're not just a little messy, I get. But let me try and redraw. There were these points which you're given, and here it's generally okay to think about them as points in RD. In fact, R2 has most of the common structure. I have these black data points, and I want to find the clusters. And I did this by choosing some parameter, some radius parameter, and then there's also some midpoints parameter. And what I do is for every data point, I want to link it to build a graph between every other data point that is within this radius. Okay? So how would we do that? We can ask a similarity query or a nearest neighbors query that we talked about in the previous section for each data point and retrieve all the nearest neighbors. And maybe I do this exactly, and there are ways you can be a little bit conservative and then throw out the ones that are actually too far away, or they're exact algorithms in 2D. I can do this I can do this in logarithmic time per data point returned. But I find all the points within the distance, and then I draw an edge between them, and this builds a graph. If it's a metric, that means it's symmetric. That means if this point is within a distance r of this one, then it's the same the other way, so that I don't need to worry about the direction on the graph. And that's the initial graph, and then I count the degree. The degree is the number of edges each vertex has, and that determines whether it's a core point or not. That degree is high enough, that's the second parameter.
So do we arbitrarily decide kind of that degree threshold that's...
Yeah, these are parameters that you give to the algorithm, and you're kind of stuck with them. You can rerun the algorithm with different parameters after you've run it with these parameters. How do you choose those parameters? It's a modeling choice.
So as a kind of, how do we know when a cluster is a good clustering? is a kind of broad question, I guess.
Yeah, that's
because it seems
a
like
really
we can
good
change a lot of these parameters, and we can get all sorts of different kinds of clustering, schemes. But it's like, how do you?
Yeah. So with like the assignment-based clusterings, there'll be a single parameter k. That'll be the number of clusters we have. You can do something similar with the other parameters. It's a little bit more complicated. Maybe you fix one and play with the other one. But you can run the algorithm multiple times, different parameters, and then look at the output. And I'll give some insight into that, maybe in the lecture today, maybe in the one on Monday, which I think will have more slack in it. But there's not a good answer to that question. Okay, we'll see with like regression, which we'll talk about soon, in like 2 weeks we'll start talking about. Then you can use kind of cross-validation to actually measure how good things are. And this is kind of like a uniform, unambiguous measure of how good it is. That is kind of universal across the different algorithms. Clustering is kind of, there's lots of algorithms because there's no way to say, well, this one is necessarily better than the other one. Part of it is this one looks good. Part of it is I showed this one to my boss and he thought, or this scientist I'm working with, and they thought it made sense to them. So that's the one I went with. It's kind of, clustering is, it's mainly an exploratory data analysis technique, in that it's useful for initially looking at your data to kind of see if some structure pops out of it. It's usually not the end step of an analysis, right? I usually don't run it and I say, okay, it turns out I have 4 types of customers, and these are grouped together, these are grouped, and they're very different from each other, right? And it's obvious. If I try to do 5, then it doesn't look right. And I try to do 3, it doesn't look right. But there is exactly 4, and I'm done. That's rarely the case. It could be the case. It's the case in some of the examples I'm going to draw on the slides, because those are the examples that kind of illustrates what it's supposed to do. But as I showed in this lecture, I think a lot of data sets will look kind of like this, right? There's a bunch of data kind of in this big smear, is what I will call it, right? And it's just like, there's not like these group structure like I have in these red circles here, which ideally is what you would like to see, but sometimes it looks like that. So whatever clusters you get out of that are not really telling you a lot of information. Yeah.
So if you're in the case of like a really high dimensional data set, you can't use your visual intuition.
Yeah.
How do you know when not to attempt to cluster?
You can always attempt clustering. So we'll see something with the value k. If you and there's this like elbow technique, whereas I increase the number of clusters, the cost function decreases rapidly and then it levels out. And if you see that pattern, that kind of indicates there are clusters. Otherwise, it's usually not. And there will be dimensional reduction techniques that we'll look at later in the semester. We'll say, if I assume I know clusters, I've given clusters, find the best low-dimensional representation, Euclidean representation of the data, maybe 2 or 3 dimensions, that best separates the clusters. And if I can get that representation, and if I still can't see the clusters, they're probably not there. There are other techniques that I won't talk about, like there's like this T-SNE technique, which I'm not a huge fan of, that will try and force clusters. It will give you a visualization that tries to show clusters, even if they're not necessarily there. And that's why I'm not a big fan of it, but it's become very, very popular. Yeah.
So with the core points clusters, a little bit confused on what you consider in clustering. So
yeah. Okay, so
if you identify a core point.
So identify the core, this is a core point,
Okay.
then every point it's connected to is in the cluster.
What about?
And then this point is not connected to a core point, But if it's connected by an edge, I can decide to add it into the cluster if I want to. But I wouldn't put these points up here in the cluster because they're not connected to any core point. The idea behind this clustering is that dense regions should be clusters, and sparse regions are just noise. And so if there's no dense region nearby, then it's not a cluster. Where this has a dense region nearby, and sometimes I get stuff kind of on the tail, but if it's connected, then I'll include it.
So if two core points are connected together, they're considered as part of the cluster.
Yeah, the connected parts of the graph are going to be in the same cluster. Yeah.
So during the lecture yesterday, we talked about clustering with regards to a distance, right?
Yeah.
But then when we were talking about distances, you said if we have data that is not of a consistent unit, then maybe a distance doesn't make sense. Can we still cluster in that case?
No, I mean if your distance doesn't make sense, then you're already kind of playing with black magic, right? And so we will later in the semester we'll talk about if the distances, if the units don't align, what can you do? And you can kind of learn a metric, one of these Mahalanobis metrics, and then you have a distance which hopefully makes sense, and then you can use that within your cluster. Okay, but you'll need a little bit extra information to do that. We'll talk about that after spring break.
So I had a question about centroids. Is there a good, how exactly are centroids like found? Because I was thinking about what if you had a bunch of data points that are represented as like a list of k-grams, where it's like a set of characters.
Yeah, we'll talk about this a little bit. So the whole lecture today is meant to be about clusters defined by representative points. Okay, and so we'll talk a little bit more about this today, and maybe we can delay that question a little bit. If you still have it, we can maybe come back to it. That'd be okay?
Yeah.
It turns out there are lots of ways that could be useful. If you can take the mean, you do that. But if not, there are other things you can try to do. But well. Yeah. Okay. All right. So let me just re-review quickly. We're going to be given an input, which is some set x, okay? And we're generally, just for simplicity in the lecture today, we're going to say that this is going to be, let's say, a subset of RD, but really this could be any subset of objects. These could be each element, each data point, say xi in x might itself be like, say, a set, and we can use the Jacquard distance then, or they could be documents, or they could be graphs, they could be these other sort of representations. Okay, and we're given an input, some data set, and we're given a distance d, which goes from let's say more generally. And making noise. The speaker's on. Okay, good. Or the microphone's on. Good. So into some value. I'm giving some distance. This could be a different metric space instead. We'll generally talk about if this distance today is going to be is going to be a metric, and in some cases, we're going to restrict the metric is going to be the Euclidean distance. Some of the algorithms will only work with Euclidean distance, some will work just with any sort of metric. Okay, and then just to repeat the statement, the goal is going to be a set of these clusters, S1, S2, Sk, where each Si is going to be a subset of X. Si intersect Sj is going to be the empty set. And in general, we're going to say that the union over all of Si's, this is going to be equal to full set, right? So this is going to be a decomposition of the points into these subsets. these are going to be the clusters. Okay, so these are my clusters. This is the output here. Okay, yeah.
Sorry, I might have missed it. Is D specifically a metric or?
In the lecture today, we're going to focus on when it's going to be a metric. You could run this when things are not a metric. You can run the same algorithm, and if it's not a metric, it will still kind of run. You can do it, but we will be able to say something about, well, it's going to work this well as long as it's a metric. There's some operations I won't be able to do unless it's like Euclidean distance in some cases, and we'll talk about alternatives. And this will come to your question about the centroid or other representative points. Okay, the change we're going to make today is assignment-based clustering. So I'm going to have these clusters S1, S2, up to Sk, and for each of them, I'm going to have a center, and I'll use C1, C2, up to Ck. Okay. I think in the different notes, you use big C and small c and uppercase C, or small s and uppercase s. Here I'll write them C and S so that you can it's easier to see if I'm writing upper or lowercase when I'm writing on the board here, okay? But I've got these centers, so every cluster is going to come with a representative center. Okay, so this restricts the type of clusterings we're considering. The lecture that I gave Monday did not have this restriction, although we considered some versions that acted this way. So these are representative points. Okay, and now I'm going to call this set. Let's call this set. Change my notation a little bit here. Okay, so let's call this set uppercase C. Okay, and if I do this, and so the next thing I'm going to find, and let's call this a nearest so a like nearest neighbor function. We'll call this phi of C. Okay, phi of C, and this can be applied to. All right, so this is going to be applied to, let's say, RD, although this could be the more general metric space, and it will return an element of this set of the centers of the representative points. Okay, so in particular, phi of C of a point X is going to be equal to the arg min Ci in uppercase C of the distance between X and Ci. Okay, so was a picture of what does this look like? C1, C2, C3, C4, and say C5. And this is this Voronoi diagram that we talked about in this nearest neighbors part of the class. Okay, and so every point, if a point X is here, it's going to map to C1. If a point X is here, it's going to map to C3. I'm dividing up the plane, or in general the metric space, into these cells, and basically I return its assigned to this cluster, right? So the idea is that I'm going to have these representative points, and then underneath this, I'm going to have a much larger set of these data points, right? And assuming these are going to be what the input data point set X is, right? If the black points are the input data points set X, then they're going to be assigned to the closest point here. And so in order to understand the structure of the clusters, I just need to know these representative points, and which cluster each data point is in is going to be defined by this phi function.
Sorry, what is argument refer to?
Yeah, oh, okay, yeah. So if you haven't seen this before, if I have a function, a min over a set, then it's gonna try plugging in every object from the set C into this distance function in this case, but this function, and return the minimum value. But when I put an argmin, it returns the element of the set which minimizes that. Okay, so it returns the argument of the minimization. So it returns the cluster center it's assigned to. Right, so this is assigning it to its nearest neighbor among the cluster centers. Yep.
How are the representative points chosen?
Yeah, so that's now the whole clustering algorithm. Once we have this formulation, is how do we choose the representative points? That's the whole challenge now, right? So now I'm going to tell you how do you choose those points. But once I choose those points, I have everything else. Everything else is implicitly defined by those points, right? So now I've got a compact representation of the data of everything hopefully mapped to its closest point. Think of this, I can, if there are a bunch of points all right around here, then this is a good representative of all of them. That's the concept behind it. Okay, yeah.
In your last example, or on Monday, we talked about outliers, that you can use it for outlier detection.
Yes.
Does this not allow for outlier detection because every point is put in?
Yeah, so we will discuss that.
Okay.
Yeah. So certain ways of doing it will be more susceptible to outliers than others. And maybe that's good for finding the outliers, maybe it's just annoying. Right? Okay, so now that we have this phi function, there are going to be kind of a few different formulations of this. The goal is now to find, right, this set C, which is C1, C2, up to CK. So we'll say K is given. So we're told there are going to be K clusters. K is a parameter that's given to us. Just the same way with dbScan, there was the radius and the min points. There are some parameters which are given to us. In this case, it's K. Okay? So we're told this, and now we want to find these, but how do we want to we want to set this up as a specific optimization function. What defines, what in fact makes a good C? Now that we have this kind of simplified form, we can specify this a bit more. Okay, and so there are different formulations. Okay, and the most common one is called the k-means formulation. Okay, and so the k-means formulation is trying to minimize call me. Okay, my phone number is from out of state, so I know if there's a phone number from that state, it's spam. Okay. I don't know if do you see the phone call come up there? No, okay, good. And my iPad is, someone tried to call me in the middle of lecture. Okay, good. So that's minimizing the distance between X, this point X, and comma, and phi of C of X squared. Okay, so this is the k-means formulation. I want to, for every day, I'm going to add up this for all of the data points. For every data point, I'm going to give it a score of how well it maps to the cluster. And I'd say I map it to whatever point it's assigned to. Right, so if I have a set C, I map it always to the closest point. That's encoded within this phi function up here. Okay, I map it to its closest point. I look at that distance, and I square it, and I add all these up. Okay, this is the formulation for k-means. Yeah.
What was the reason for squaring this? Why do we square it?
Yeah, we will see if you use Euclidean distance, then there's a really simple algorithm that everyone uses. But that algorithm only works if I use the squared distances, is what my objective is.
Okay.
And we'll get to that. You saw this last semester.
I just couldn't remember the. Yeah.
Okay, well then hold on. So, okay. And so this one is very common. We'll just say D equals Euclidean. Okay, in this case. You probably would only use this formulation with the squared if you're using Euclidean. There are a couple of other cases, like if your data points are on a sphere, then it kind of makes sense to do it too. But we'll see there's a step you want to do, which you can do under this formulation with Euclidean distance that you can't for other formulations. At least not easily. And then you want to do something else probably. Okay, so then, but there are other versions of this there's case center. Okay, so case center is trying to minimize the max of D okay, just the maximum distance. So I look at all the assignments of a point to its center over all the points in my data set, and I look at the assignment. I take whichever distance is the furthest. I want that to be small. So I'm minimizing the maximum over all of these, right? So it's a min-max formulation. Okay, and so this for outliers, if I have an outlier, this is going to be controlled by the outlier. If I don't handle, it's going to have to grab those outliers. Okay. Okay, and again, this is not argmax. This is the max that's returned the value instead of the argument. Okay. Okay, and then the k-median formulation is to minimize, again, the sum here, but now I'm not squaring. The minimum, the k-median is without the square. So this is the version that might seem more natural, but it turns out this one's harder to solve. There's not as simple of an algorithm to solve this as the k-means. Okay, and then there's one more, the k-medioid, and this is to minimize, again, the same objective function as the k-median. Okay, this is the same, but I restrict that the center set is going to be a subset of X. Okay, so the k-medioid restricts that the centers I consider are going to be a subset of my data points. Okay, so this is a restriction, but it turns out, this one you can solve for because now I only need to consider data points to be the representative points, where the other ones don't have that restriction. Turns out for k-center, we're going to solve it with the representatives, but for k-means, we don't have to, and that actually gives us an easier way to solve this, but only for Euclidean distance. So when you don't have Euclidean distance, you actually probably want to do this because I don't want to deal with the square. The square really doesn't help that much unless you're kind of like a Bayesian perspective. Then there's reasons to have a square there because it goes with Gaussian noise in some ways. We're not going to get into in this course, but if I this one's going to be more resistant to outliers because I'm not squaring a distance, I'm just looking at it. But if I take a representative, then I can solve this one as easy as I can solve that one because I basically have to check the representatives, the potential representatives, in that way. Yeah.
Is that an I or is that a D for the last?
This is, you're right. That should be a phi. Thank you. Good. So, thanks. Okay, so I'm going to get to k-means, but I actually, there's something called Lloyd's algorithm, which we'll get to, which is the kind of sometimes referred to as the k-means algorithm, just because it's what everyone usually uses for that. It's very universal for clustering, probably over 50% of the time people say I'm clustering, they're actually running Lloyd's algorithm for k-means. And it's a very kind of clever, simple algorithm, but I believe the k-center algorithm, okay, so this one generally use Lloyd's. There's going to be an even Gonzalez. There's an even cleaner algorithm for k-center, which I like even better, and works almost as well, and is even simpler, way simpler than the stuff we talked about on Monday as well. So I'm going to start with that one. Okay. Okay. So we'll start with this k-center formulation, where we want to minimize the longest distance of an assignment. Okay? Okay, so Gonzalez algorithm for k-center. Yep.
So just to clarify, the minimization is basically choosing the optimal C values.
The set of k representative points. Yes. Yeah, I'm trying to choose. I want to find, right? The goal is to find here, right? This is my goal, and then, but how do I really specify that goal? Because I've restricted the problem to have this structure, I can write down these specific minimization problems, and these are like it's you almost never hear of one outside of these four, right? Okay, great. So the Gonzalez algorithm for k-center clustering. Okay, so the main idea here is to build the set C. So I want to build the set incrementally. Okay, so I want to go from C1 to C2 to CK, which is going to be equal to the set C. Okay, so I'm going to build these in a series of k steps, and after I have k steps, then that's going to be my final set, and I'm going to have that the size of CI is going to be I. Right, so I'm going to start with the set of centers of size 1 with one center, then I'm going to add a second center, then a third center, and fourth, and so forth, right? So I'm going to add my centers, or my sites, 1 point at a time. Okay, so the algorithm is going to be quite simple. I'm going to choose C1. This is the first center. Basically, this can be so I can choose this first one arbitrarily. Okay, it's there's not even like any really meaningful heuristics for choosing the first one. I just choose one. In your homework, choose the first point in the file. Basically, is what I'm going to tell you to do. And the algorithm is deterministic, so once I choose this one, it could be random, but once I choose this one, there's no like randomness in the algorithm. Okay, and so in general, and then, okay, so now I'm going to have a for loop for, let's say, j instead. Let's say for j equals 2 to k, right? So, and so this means that my initial center set 1 is going to be just this single point. Okay? And then I'm going to set Cj, which is the next center point I'm choosing, to be equal to the arg max of all the data points of the distance from x to phi of the set C of j minus 1 of x. Okay? This is the whole algorithm. Okay, so this step is encoding a few things going on here. inside of this step here. So let's go through an example, and I think it'll be clear. Okay, so I'm going to start with some data points that look like this. And to really understand this, it's important to make k large enough, because kind of the dynamic changes a little bit around the third step. Okay, so I'm going to pick the first sum point here as C1. This will be the first point. Okay, and now, okay, so this is arbitrarily. And now the second point I'm inside the for loop now. The second point is going to be the furthest point from, I'm on j is equal to 2, so C of j of 2 minus 1 is 1. And that's just this set, right? This set of centers. So the furthest point from this one center, so that's going to mean the furthest point is going to be out here. This is going to be C2. Okay? So now I've got two centers. If k was 2, I would stop. That would be it, right? And then I would assign points to the closest center. Okay, but I want to keep running this. Let's run this further. I'm going to run this for the third point. Okay, I'm in the for loop again. I want to find the furthest point from either of these. Okay, not the furthest point from this point alone, but from either of these points. Okay, so I kind of need to check all of the points here and find which one is furthest from either of these. So it could be, say, this point would be assigned to C1. Right, so I can assign it to the closest point. I look at this distance, and I want to compare it to maybe this one. Would this point be assigned to C1 or C2? It's pretty much in the middle. So maybe I'm going to say this point is the furthest. Okay, so maybe this will be C3. Okay, this is further from C2, but it would be assigned to C1. Right, so I want to do its assignment and look at its cost, right? And what I want to minimize is this longest edge. So if I pick the longest one, the cost has to go down. Okay? And then I can run this one more step. Now, all these points are assigned to C3. These are all assigned to C2. These are all assigned to C1 or maybe C3. And these are all assigned to C1. This point looks to be the furthest. I can put C4. Okay, this is the longest distance. And you see the distance is dropping a lot. Now maybe the furthest point is probably, this one's assigned to C1. That's pretty far away. So I'm going to add this as C5. Okay, in the back.
So each time you recalculate the distance against every other point that's left.
Yeah, you could do it that way. What you can do is you can maintain an array, and for every point of size n, for all my data points, for every point assign store in that array the index of the closest point that I've seen so far. And I just have to check against the previous closest point. So I just have to update this array. So I don't have to recheck all the distances again. I only have to check the ones that were reassigned. And then keep track of whichever one is the smallest. And so this I can do in linear time per round, and I have k rounds. Yeah.
So I'm a little bit confused. You were saying some points are assigned to C1. Where does that assignment happen if this algorithm is just choosing what values?
The assignment is implicit. It's implicit. So every time I store this set uppercase C, right? And for every data point, I ask what center is it assigned to? Well, either I can store that assignment based on I've pre-computed it, or I can recalculate the distance to all the centers if I want to. Right? So I don't need to store that representation, but I can. So it depends on if you're actually, so there are two uses here, right? If I'm actually implementing it, I probably want to store a representation of what's the index of the center every point is assigned to. For every point, I want to store its assignment. But once I'm done with the algorithm, I might just want to store the centers. I don't want to store all the data. I want to get a compact representation and so I might throw that away. because it's using up all my memory.
So you said like you were picking C3. You didn't go all the way across to say like the C4 point was the furthest from C2.
Yeah, right. Because I knew it would have been assigned to C1. So it's the length of the edge of C4 was not to here, because I would have assigned it to C1, because that's closer.
So you're looking at the max of, when you're trying to find the max, it's only of the points that are assigned to the value.
Yeah, right. That's encoded in this phi function, the distance from x to its assigned center. So there's a lot kind of going on in this one statement here. This phi is inside of it has a min, has an argmin, right? So that argmin is inside of this argmax, right? So it's it's a compact way of writing it, it's clever notation, but it kind of encodes a lot of information. Yeah. Okay, there are more questions there first? Yeah.
It seems like this is really vulnerable to outliers.
Yep, yeah, so if you have an outlier, you are going to grab that outlier if it's far away. Yeah, maybe that's good. Maybe you want to identify all the outliers, and then I can say, well, there are very few points assigned to these centers, so I'm going to kind of ignore them. That'd be one thing you could do. But if you look at this, it's not the algorithm's fault, it's the formulation's fault. The formulation said, this is for a K center, I want to minimize the max distance. That's what I care about, right? Let's say I've got a population who lives in my city. I need to service everyone with the fire department. I want to make sure that the fire department is within a distance of a small enough distance from everyone, because they need to be able to get there quickly if there's a fire. And there's some law passed that no one can be more than 5 minutes from a fire department or something like that. So this is basically what I need to do. I need to run this algorithm until my distance is less than 5 minutes. That's how I measure distances, right? So if someone lives way up in, say, in Emigration Canyon, for instance, I forget if that's in Salt Lake City or not, but there's a fire department up there because there aren't a lot of people who live up there, but they need a fire department. Right? So that's how you solve it. Yeah. Yep.
So if you were to use a different one of these formulations, would the results be not useful, or would they just not make sense?
Well, these are formulations, these are objectives, and this algorithm naturally pairs with this objective. Right? I can calculate the cost of any of these. Right?
What happens if you do pair? How would you interpret those results if you use?
Well, so like, the K-median, for instance, is not going to be very sensitive or as sensitive to outliers. I still may want to choose them because that one outlier may have a large cost if it's not one of the centers. But it's only 1 point, so it doesn't account for that much. So if I ran the Gonzalez algorithm, I'd end up picking that outlier as a center when that was pretty wasteful. So it's not really trying to optimize this objective. Right? And which objective is the right objective? That's a modeling thing. If it's the fire department problem, well then maybe I need to use the case center. There's a law saying I need to satisfy that. But otherwise, maybe this makes more sense. If you're thinking of Gaussian noise, there's a reason why the k-means make sense.
Is Gonzalez more susceptible to the first point that you choose than some of these other ones, or is it just kind of eventually even out?
Yeah, so they're all kind of susceptible to that in some way. I can say that there's something known if, so I can say if D is a metric, then I can say that the output is a 2 approximation of the optimal. Okay, and this is including using an arbitrary first center. Okay, so what does this mean? It means that if I ran the optimal assignment, let's say k equals 5, perhaps the optimal assignment put a point like in the middle of all these clusters. Right? And this is kind of be better. Gonzalez tends to put them on the edges of the clusters. Okay, but if I put it in the middle, and this was the best thing I could do, then the longest assignment here is now this instead of this distance. That's off by no more than factor 2. Right? So it's even, no matter where I pick the first center, it's never off by more than a factor 2. And in fact, for arbitrary metric spaces, it's shown that it's NP hard, actually, to do better than a 2 approximation. And you can do slightly better, like in Euclidean distance in the plane, you can do like a 1.87 approximation with the polynomial time algorithm, but you can't do better than that. Okay, so you really can't do much. In the worst case, you can't do much better than this. I can run this, and then I can try and optimize it a little bit, but this will do pretty well for this objective. And in practice, it generally works. I basically have the right clusters, right? I may not have exactly the right representatives, but I roughly have the right clusters here. And that's kind of what this guarantee says. If there are going to be K clusters, I'm going to find those K clusters. Yeah.
So what's the complexity of that algorithm?
It's if you write this algorithm like the way where you keep track of the assignment as you're going, you can do it in O of K n time. Okay, so I just need to, on every pass, I have every point I have to the best assignment, and on every pass there are only K passes. I recheck the assignment to the most recent cluster, and I keep track of the max. That max ends up being my new center. And then I repeat that pass. So I only need K passes over the data. Each pass is linear time. And in the notes, I actually write out the pseudocode in even more detail, so you can see how to do that. But so you can get this to run very fast, right? Usually K is small, so it's pretty fast out. Okay, cool. So I mean, this is a really simple, clean algorithm, but it's susceptible to outliers, as many of you have pointed out at this point. Okay. Okay, so let's talk now about Lloyd's algorithm for k-means. Okay. So Lloyd's algorithm for k-means, remember this is the k-means objective minimizing the sum of the squared errors. Okay, and this one is going to be it's an iterative algorithm again. It's going to have a series of steps, but it's not going to sequentially build up C. It's going to start with C. Okay, so the first step here is I'm going to somehow choose K points, and this is going to be my set C. Okay, so I'm somehow going to choose K points. Maybe it's arbitrarily. But we'll get back to how do we choose the first. For this, in this case, it's more important to choose these because k-means this algorithm can do really poorly if you choose these incorrectly. Okay, as opposed to because of the k-means objective than the algorithm itself. Okay. Okay, and then I'm going to repeat the step until some condition is met. So 1A, I'm going to say for all x in x, I'm going to find phi of c of x. Okay, and what this is going to do is it's going to create these sets S1, S2, up to Sk, right? Where Si is going to be x in x such that C is equal to the ith center, where Ci. Okay, right, and this is so I'm going to create these sets. Right, so for each data, now I'm explicitly building into the algorithm. I'm writing down, I'm going to find the best assignment. Okay, so I'm going to start with the set of centers, and then I'm going to find the best assignment for all of them. Okay, this step is pretty natural. Okay, okay, one, 1b, okay, for all I in 1 up to k, I'm going to let ci equals the average of si. Okay, and so here it's important that, so d equals is going to be the Euclidean distance, and that means that I can actually compute this average as, when I mean average, I mean exactly this average like this, where I'm going to basically do, this is a coordinate-wise average. These are vectors, but every coordinate I do the same thing. I'm going to add up all the values of each of the x's in the set that's assigned to the center, and then I divide by the number of points that's in that center. That's an average. This works in any dimensions. For Euclidean distance, the special thing is this is the point that minimizes the sum of the squared errors. Okay, so there's some magic here. This only works for Euclidean. This is the arg min, let's say z in Rd, that minimizes x in, let's say, si of the Euclidean distance between z and x squared. Okay, so if I want to find the point that minimizes, the point z, which minimizes the sum of the squared distances of all the points in my set si to this point z, it's always exactly this average. So because this was my objective function, I know this is the right thing to do. If I know all the points assigned to one cluster, then the best representative is always their average. Okay, so for this k-means objective, this is basically the right thing to do. Okay, and then this is basically an until, let's say, the set of these clusters is unchanged, or the change is somehow small. So if this is an iterative algorithm. It's going to keep evolving as I'm running this, and either it's going to get to a fixed point and it'll stop because I've got the right answer, or maybe it's not the right answer, but it's stopped. So then I shouldn't keep running through the loop, or the centers are changing by a very small amount, and I'm like, okay, it's probably pretty close. Okay, usually. Usually, I would say less than 20 steps. Probably even 5. I've asked you to do this on the homework. You probably run less than 5 steps. Okay. Okay, but you could run 20 on the high side, and then you don't need to check. Just go run for 20 steps. Okay. And again, each step I can do in linear time. So basically, the number of, assuming I can do the nearest neighbor, if k is a constant, yeah, so it's the number of steps, let's say 20 times k, because I need to find the nearest neighbor. Maybe I can do that faster with the day structure, and then times n. Right? So again, it's a pretty fast algorithm. I don't have to worry about anything like n squared or n cubed complexity on these algorithms. So as n gets big. Okay, yeah.
So how do you choose the initial points?
Okay, good. Yeah, great. So I want to talk about 2 more things in this lecture. 1, maybe 3 more things. How to choose these initial points. 2, I want to go through kind of a little example of this. And 3, I want to talk about some of the messiness and the complexity of actually implementing this. Okay, so let's, maybe I'll go through an example first. I'll make sure, but I want to get back because this question is actually interesting, and there's actually a pretty good solution for it. Okay. That we did not see in 3190 for those who were in that class. Okay. Okay, so let's go through just kind of an example. And so let's say, and this will, okay, so what's going to happen here? I'm going to start with, let's say I've chosen 3 points that happen to be chosen these 3 points. K is 3, right? So K equals 3. Okay, so what I want to think about doing here, and the way I like to visualize this, is using the Voronoi diagram of these 3 points. Okay, so what I can do is I can divide these dividing cells. Okay? What this is saying is that all these points and most of those up there are assigned to the center. Let's call this C1, C2, and C3. So most of these are assigned to C1. So what's going to happen is that C1 is going to move to about here. Move to there. C3 is going to move to here. Let's say that's C3. And C2, it's got 1 point from up there in the top left cluster. So it's going to move over this way, but not all the way. C2. Okay? And so then I'm going to redraw this Voronoi diagram. And things have shifted a little bit here. Okay, so this is the new Voronoi diagram of these new points. And this defines a new assignment now. Now points are assigned differently before. Okay, so C1 moved down, so even though C2 moved further away from those points, because C1 moved down, some of those points are now assigned to C2. Right, so C3 is pretty much going to stay in this same spot, but C2 will now move out to here, and C1 will probably move down to here. Okay, and I'm going to repeat this again. Let's say, just to make this quick, let's say it kind of goes like this, and say like this. Okay, and now I've got the perfect, I'm going to move them basically all to their best center. Okay, and the Voronoi diagram after this is going to be just like I would hope. Okay, and so now I've got the right assignment. Does it kind of make sense? It gets a little messy drawing these things, but you're going to see it in action. Okay, so I keep reassigning the centers and then reassigning all the points. Okay? And so kind of the key thing to see about this is this k-means objective function is going down every step I do. Every time I reassign the centers, I'm fixing the centers. I'm keeping the assignments the same, but the cost of that center is going down. And when I reassign the points to the closest center, well, that cost is going down too. So the cost always goes down. So this is converging towards the right solution. So I can never get stuck in like an infinite loop, because that would require the cost to go down and then back up again to get to a previous step. So I have to be converging towards something. Yeah, but it could get stuck in a local minimum. Yeah.
So I guess this might be a fun back to extent. Like, what if you choose K that's like too small and you end up like wedged between a cluster, like the Voronoi diagram has an edge, then it's a wedged in a cluster, it's flipped it in two. Like, how would you know that you're in that situation?
You could try rerunning with the larger K and see if the cost went down significantly. Yeah, that's, or you could look at the variances. Like if there's a way of trying to fit a Gaussian distribution on top of each of the assignments, and the Gaussian distribution has a really high variance, you know, and maybe the fourth moment is large, that would correspond with this, so you can look at the fourth moment, I think. I think that would be large in that case. And that'd be a good indication you'd split it. So there are statistics you can look at these clusters. You know, you could look at each cluster. Let's see if I run a clustering algorithm on the cluster and see if it brings the cost down a lot. And you know, there are different things you can try and do. But in general, the general solution to these things is rerun with a larger k and see if the cost goes down. Okay, great. So this is roughly how it ran. I want to show you one kind of more example. Let's say the cost function looks like, right? So this is the data set, and let's say I have k equals 3, and now let's say I pick as my 3 clusters centers here. Okay? What's going to happen is that it's going to be a Voronoi diagram that looks kind of like this, and it's going to get stuck. It's not going to update any of the centers. Maybe it moves these two in a little bit closer, but it doesn't reassign any points. But this is, if you look at it, it's not the right answer, right? But so this algorithm does not necessarily find the right answer. It can, Lloyd's can get stuck in local min. It can get stuck in a local minimum. It means it thinks this is good. It doesn't see a way to improve it with any of the steps it can do, but it's not the right answer. The right answer would be a point here, a point, another point up there, and a third point up here. But I somehow got 2 centers over here. Okay. So there are lots of these kind of weird issues that come up. There are other cases that can come up where I could somehow, in the course of the algorithm, have a point with 0 points, a center with 0 points assigned to it. What should I do then? Right? I need to have, like, if I write code for this, I might need to handle a special case if this happens. Right? So there's all these kind of messy things that have to be done. In general, if that happens, instead of writing a special case, I would just reassign the initial placement of the centers and start over again, instead of writing all these special cases. If something weird happens, I don't know what to do, just restart the algorithm again and try running again with the different initial assignments. Okay. Okay, but the real limitations are messy because of weird issues like this. Okay, so if we go back to this, okay, and if you're implementing this, I would again keep a data structure of an array of, for every data point x, the center it's assigned to, and then just use that inside your data structure implementation. It'll be a lot easier. Store that instead of recalculating this every step. That'll make the calculations a lot easier for you. Okay, so let's go back and say, how do I choose the k points initially? The initial choice of the k points. I said if you get into a weird situation, I should go and redo this step. What would be good ways to do this? Yep.
Pick random numbers.
Yeah, so I can take random points. Yeah, so let's say so choose initial k centers. Okay, so a pretty good choice is pick random, and I'm going to say a subset, which is a subset of x. Pick a random subset of the points, right? So pick random indices from the set x. Make sure they're distinct. This actually works. So this works reasonably well. It doesn't always work. though, I mean, even kind of if I ran it over and over and over again, it's unlikely if there's one cluster here, there's a really big cluster here, and then there's another cluster out here. There are 3 clusters, 2 small ones and 1 big one. It's very rarely going to pick one point in both of those 2 small clusters, or send a point out there. Because if there are like 1 million points there and 100 points in each of those, it's rarely going to pick a point in both. And as k gets bigger, this can be more of a problem. And so it's going to divide up the middle cluster, which is not going to be the optimal solution. Maybe it's a reasonable thing to do, you know, but it turns out not to be optimal. So this doesn't always work. Okay, but this is a good initial guess, and I can keep. And for most data sets that the clusters are roughly even size, this will actually work pretty well eventually. I'll eventually pick a starting point that will be close enough. But it won't always work, yeah.
Maybe this is a little cheeky, but we could use the Gonzalez algorithm.
Great, yes. So use the use the Gonzalez algorithm as the initialization. That's great. In fact, in this situation here, it will succeed. Right? The Gonzalez algorithm will definitely place one of the centers in each of these sets. That initializes, gets the right cluster, the right basic grouping, and then Lloyd's algorithm will optimize the actual location to be right in the center. That's great. So this is actually a really good idea. Right? So this works really well most of the time. Okay? So the Gonzalez algorithm is close, but let's say that there are really kind of 3 clusters, and they're like 1 million points, and there's 1 outlier out here, right? And this is a case where actually the k-means will be better off if I choose 3 points in these centers and not in the outlier. But if I start with the point in the outlier, it might get stuck out there with k-means. Okay, there are other situations like this. So outliers can be problems with the Gonzalez where it's the wrong objective function. If the data does not have many outliers or they're not too extreme, then this will actually give you the right solution. The other downside is that it's deterministic. So I can, every time I run it, it's going to give me the same thing. I can't like re-randomize it like I could step 1 and hope eventually it gets the right answer. I can't get something that if I run over and over again, I'm going to get some kind of concentration results or some like eventually I'll hit this event. Okay, so what I want to do is somehow combine these 2 together. And there's an idea which exactly is combining these 2 ideas called k-means plus plus. Okay, this was back when C++ was a popular programming language, and the people named things plus plus. I'm friends with the authors of this idea. I think that's where it came from, and it's basically combine these ideas together. And the idea is to okay. Well, let me write this on a new slide. K-means plus plus. Okay, it's going to be like the Gonzalez algorithm. So step 1 is I'm going to choose C1 arbitrarily, where C1 will be an element of the data points. Okay, so I'll choose an arbitrary set here, and again I'm going to build up the centers incrementally. And now for I equals 2 to k, then what I'm going to do is I'm going to choose Ci, right, from x. This is going to be a point from x with probability so probability that's going to be proportional to the distance of x to the assignment of Ci minus 1 of x squared. Okay? So instead of picking the longest distance, I'm going to calculate all of these distances, I'm going to square them, and then I'm going to sample from the data points where I'm going to more likely pick the points that have a larger distance. And it's exactly, or the larger squared distance, exactly kind of essentially their cost. So if I have a really big outlier, its cost is going to be really high. I'm very likely going to pick it. But if I have another cluster that has a lot of points in it, and they have a medium cost, but there are a lot of them, it's likely I'm going to pick one of those points. Okay, so I somehow need to pick it proportional to this. I can think of, just to explain this, I can have some, let's call this for data point xj, this is going to be vj, and let v is going to be the sum of j equals 1 to n of vj, and so then the probability that I'm picking xj is going to be vj divided by capital V. Right, so that's the probability I want to choose this one. Okay, and so how do I choose a point with this probability? One way I can do that, each of these, let's call this pj. So the sum of the pj, what I know is that the sum of pj is exactly 1. What I can do is I can do this, what's called this, this like partition of unity, where I can think of having a strip from 0 to 1, and I'm going to kind of fill this in with these pieces. This is P1, is the size of P1. This is the size of P2. So the length along here is the probability I picked the second point, and so forth. And I'm going to keep doing this, right? And so this is going to be, this is PJ. Okay, and so then what I'm going to do is I'm going to pick a uniform random value, 0 to 1. Okay, between 0 and 1. And if this is going to be, let's say this is 0.55, then that's going to be here. Then this is the value of u, and I pick pj. Right, so I compute all these kind of fractional values, and then I kind of lay them out. So this point is the sum of P1 and P2. This is the sum of all the points up to Pj, right? And then I just have to, I've divided up 0 and 1, and I pick a random value, and it indexes into here somewhere, and that's how I make the selection. So there's this little, you have to kind of implement this in order, this little trick. There are other ways to do it, but this is the simplest way in order to implement this k-means plus plus. But this will kind of, if I repeat this randomly enough times, it will kind of guarantee to eventually get the right center assignment for k-means k-means clustering. And then I run the rest of Lloyd's algorithm, and it will optimize it. Okay, and this is now kind of a de facto thing. It's built into like MATLAB of all places, right? As a de facto way to run Lloyd's algorithm. Yeah, for
so if you're generating a probability distribution and then run use center.
That's right. Every time I pick a center, I have to generate the probability distribution and draw an element from it. And this is kind of this partition of unity trick. This is probably how you'd implement it.
How many P's are there?
N.
And for the number of entry points.
Yeah. Okay. So I have this.